So, hello and welcome you all in the problem solving class of the course Principles of Signals and System. I am Vivek Kumar Srivastav, a PMRF research scholar of Antenna and Microwave Research Laboratory, Indian Institute of Technology, Roper, and TO of this class. So, in the previous class, we have covered some topics such as basics of jet transform. Then we have gone through various properties of jet transform, and in the last we have seen the inverse jet transform. So if suppose jet transform is given to you, so how to find out the signal that has to apply to the system. Okay, so such problems are known as inverse problem. Okay, so we have seen all these concept in the previous class. So in the today's class we will explore some numerical, we will see some numericals based on the topic jet transform, and at last we will also go through the Fourier series. So let us start. So in continuation to the previous class, so we have seen some numericals. So in the today's class, first we will revise some of the numericals. Okay, and then we will go through the uh, next topic. Okay, which is the topics we have to covered in the today's class. Okay, so here is the first problem. So it is given that a signal is given to us like this, that is 9 raised to the power minus n un minus 7 raised to the power minus n u of minus n minus 1. So we have to find out the reason of conversion of its jet transform. Okay, so first of all, if we can see here, so this signal is basically composed of summation of two different signals. So here, if suppose uh, I'm writing here x of n. Okay, so x of n is basically a combination of two different signals. First is 1 by 9 raised to the power n u of n, and the second one is minus 1 by 7 raised to the power n u of minus n minus 1. Okay, so uh, here we have to find out the region of convergence. Okay, so first of all, we can use the previous we can use the knowledge of the previous class so as to directly find out the region of convergence. So like in the previous class we have seen two kind of signal. One is the uh, right sided signal, or and the second one is the left sided signal. Okay, so in case of right sided signal we have seen that ROC, if suppose this is my right sided signal, which is an un. Okay, so for this kind of signal ROC, we have seen ROC should be greater than R should be greater than mod of a. Okay, whereas for the case of left sided signal, which is minus an u of minus n minus 1. Okay, so for left sided signal ROC is defined as, okay, so mod of R will be less than mod of A. Okay, so if we can use this knowledge, so we can directly find out the ROC of this signal which is given to us. So like here, if we can see that this is a right sided sequence, whereas this one is the left sided sequence. Okay, so for right sided sequence the ROC will be, R will be greater than 1 by 9. Okay, whereas for left sided signal sequence, this will be left sided sequence, ROC is defined as mod of R will be less than 1 over 7. Okay, so if we plot this ROC, so this will be like, this is the real part of Z and this will be imaginary part of Z. Okay, and here is the 1 by 9 and here is the 1 by 7. So uh, the for right sided sequence ROC will be greater than 1 over 9. So if suppose this is the circle of radius 1 by 9. Okay, so ROC of this signal will be this one. Okay, whereas for left sided sequence the ROC will be, so here is the circle corresponding to the radius 1 over 7. So for this kind of signal ROC will be this one. Okay, so as this signal given to us is basically a combination of two sequence, one is the right sided, the another one is the left sided sequence. So the ROC is basically the ROC of the overall signal is basically an intersection of these two ROC. Okay, that is R1 intersection R2. Okay, so the net ROC, if you are plotting here, so ROC of this signal is basically a ring shape. Okay, so the ROC is basically a ring shape, because if you take intersection of these two, so this is basically the ROC, which is basically a ring shape. Okay, so that is how we can apply the knowledge of the concept that we have covered in the previous class, so as to find out the ROC of any general signal that is given to us. Okay, so any doubt in this problem? Yeah, so let us move ahead. So we in the previous class we also covered inverse jet transform. So in that we have seen partial fraction expansion so as to find out the inverse jet transform. Okay, so first of all let us rewind and see that why it is important to find out the inverse jet transform. So in the previous class we have seen that uh, how to find out the jet transform if a signal x of n is given to us. Okay, so I- on the contrary, if suppose x of z is given to us, so can we find out that which kind of signal is basically giving us this kind of uh, jet transform? Okay, so this kind of problem we can easily solve by using inverse jet transform. Okay, so in the previous class we have seen that one method that we can use is the partial fraction expansion. Okay, so we also seen one numerical, but here I am just taking one more example so as to make it clear to you. Okay, so here is the numerical that we have to find the inverse jet transform of this x of z that is given to us, and also ROC is also given to us, that is mod of z will be greater than 1. Okay, so we have to determine basically here the inverse jet transform. Okay, so let us uh, solve this problem. So first of all, if we can see here that x of z is basically defined as a rational function, okay, of z in both numerator as well as denominator, if you can see here. Okay, so both numerator and as well as denominator is basically a function of z. And for this problem, okay, here if we can see that order order of numerator polynomial is 2, whereas for denominator order of denominator polynomial is also 2. Okay, so order is basically represent the highest degree of z. Okay, so if you can see here, like x of z is given to us 1 plus 2 z raised to the power minus 1 plus z raised to the power minus 2 over 1 minus 3 by 2 z raised to the power minus 1 plus 1 by 2 z raised to the power minus 2. So if you multiply both numerator as well as denominator by z raised to the power 2, so the net function that you will obtain is z square plus 2z plus 1 over z square minus 3 by 2 z plus 1 by 2. Okay, so from here we can see that highest power of z is 2. Okay, because z raised to the power 2 is there, so that's why I'm directly writing here order of polynomial is 2, and here for denominator polynomial it is also same, that is 2. Okay, so for determining the inverse z transform using partial fraction expansion method, we have to first uh, check whether the polynomial, whether the function that is given to us, that is transfer function given to us, is a proper rational function or not. So we have to check basically first of all whether the given uh, polynomial, or say uh, rational function that is given to us, is basically a proper rational function or not. So basically there are two kind of transfer function that usually happen. One is the proper, and the another one is improper. Okay, so in case of proper rational function, the order of the numerator polynomial, so here order of numerator polynomial is basically less than order of denominator polynomial. Okay, whereas in case of improper, this condition will not true. Okay, so like here, if we can see in this problem, so here also, like, order of numerator polynomial is 2, whereas order of denominator polynomial is 2. So that's why this is an improper rational function. So we have to so for finding out the inverse z transform, we have to first determine the we have to first convert this rational function in proper rational function, and then we will find out the inverse z transform. Okay, so for that what we will do, we will first uh, divide this numerator by uh, this denominator that is given in the rational function form. Okay, so like here I am dividing the numerator with denominator, if you can see here. Okay, so like here if you multiply this denominator by 2, so you will get z raised to the power minus 2 minus 3 z raised to the power minus 1 plus 2. Okay, so now once you inverse this sign, so you will get 5 z raised to the power minus 1 minus minus 1. So now this x of z is written as 2 plus 5 z raised to the power minus 1 plus sorry, this will be minus 1 over 1 minus 3 by 2 z raised to the power minus 1 plus 1 by 2 z raised to the power minus 2. Okay, so now this rational function is proper rational function. Okay, and this is basically a constant. Okay, so we can now determine the inverse z transform for this rational function, and then we can easily determine the inverse z transform of this function. Okay, so like here uh, if we can.
Sir,
Yes,
sir,
yes.
one question, sir. I understand if it is improper,
Yeah.
we can convert it to proper with B0 plus a proper function,
Yes,
correct?
yes, yes.
Yeah. In the proper function, for example, if the denominator is not factorable,
Mm-hmm.
what we should do?
Then we
So
will
here
go
in this
for
example,
another
yeah.
method. Then we will go for another method that I will show you in the upcoming slide.
Okay, sir. No
Yes.
problem. Thank you.
Yeah. So, like now in the denominator, we are factorizing it. Okay, so once you factorize it, you will get two different factors of the denominator polynomial. Okay, so now we can use the uh, partial fraction method. So, like in the previous class, we have seen that this can be written like 2 plus a by 1 minus 1 by 2 z raised to the power minus 1 plus b over 1 minus z raised to the power minus 1. Okay, so now we have to just determine these factors, that is a and b. So that I already covered, that how to determine these factors. Okay, so in the previous class we have seen that by using this formula we can easily determine. So I am leaving this exercise for you. You can later try to check it. Okay, so after determining the value of a and b, you will get the value of a as minus 9 and b as 8. Okay, so once you put this a and b value here, so the x of z is equals to 2 minus 9 over 1 minus 1 by 2 z raised to the power minus 1 plus 8 over 1 minus z raised to the power minus 1. Okay, so now we can easily take the inverse jet transform, because here this is a constant. Okay, and for delta function we know that the inverse that the jet transform is equals to 1, whereas for unit function we know that if suppose this is a raised to the power n un, the inverse jet transform will be of the the jet transform will be of the form 1 minus a z raised to the power minus 1. Similarly, for a minus a raised to the power minus 1 minus n minus 1, this is kind of signal, the inverse the jet transform will remains the same. Okay, only the ROC is changed here. For this signal, ROC will be greater than mod of a, whereas for this ROC will be less than mod of a, that we have seen in the previous class. So by using this we can easily take inverse jet transform here. So x of n is basically defined as 2 into delta of n, because for delta of n the jet transform will be 1. Okay, so that's why here delta of n we can directly put, and here this will be 9 because 9 factor is already there, and here we can use uh, this formula. Okay, so this will be 1 by 2 raised to the power n u of n plus 8 u of n. Okay, because here a will be 1. Okay, so we can put here a as 1, so this will be equals to u of n. So that's how we can determine the that's how we can use the partial fraction expansion method. Okay, so as to determine the inverse jet transform. So there are several other methods by which we can also determine the inverse jet transform. Okay, so like one of them is power series expansion. So so as we know that jet transform of any signal x of n is written as summation n is equals to minus infinite to infinite x of n z raised to the power minus n. So this can be expanded as like x of minus 2 z raised to the power 2 plus x of minus 1 z raised to the power 1 plus x of 0 plus x of 1 z raised to the power 1 plus x of 2 z raised to the power this will be minus 1 minus 2 plus dot 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 and so on. Okay, so once you put the value of n here like 0 1 2, so you will get this kind of expansion. Okay, so now for determining the inverse jet transform you have to just determine these coefficients. Okay, you by determining these coefficients you can easily determine the inverse jet transform. Okay, so like here I am taking one example. So here we have to determine the inverse z transform of x of z. Okay, so which is given as z square into in bracket 1 minus 1 by 2 z raised to the power minus 1 in bracket 1 plus z raised to the power minus 1 in bracket 1 minus z raised to the power minus 1. So here if we can see that it has only numerator function. Okay, here denominator function is 1, so we can not be able to use the previous method, that is partial fraction expansion method here. So for that we will use this power series expansion. Okay, so first of all we will first multiply all those terms that is present here. Okay, so after multiplying you will get this kind of series. Okay, so you have to just now determine these coefficients. Okay, so like here if you can see that at n is equals to minus 2 the value will be 1, at n is equals to minus 1 the value will be minus 1 by 2, at n is equals to 0 the value will be minus 1. Okay, at n is equals to 1 the value will be 1 by 2 and 0 for all other cases. Okay, so here is the coefficient that we have obtained. Okay, so once you know the coefficient you have to just take inverse z transform. Okay, so like here we know that for delta function, okay, the z transform is defined as 1. Okay, and here we also have to take one more property, that is time shifting. Okay, so like in the previous class we have seen the delaying function, that is n minus n1, let us say. Okay, so for this kind of signal the z transform is defined as yeah, z raised to the power minus n1. Okay, so this is known as delaying, whereas advance is defined as n2, let us say. So this will be equals to z raised to the power n2. Okay, so by using this property we can easily follow we can easily determine the inverse z transform. So like here if suppose we take the inverse z transform, so this we can write as x of n is equals to delta of n plus 2. Okay, because here the signal is advancing, then here this will be 1 by 2 delta of n plus 1, then this will be delta, this is minus here, just a moment, then this will be 1 by 2 delta of n minus 1. Okay, so like here you can see that by easily expanding or say by easily using this power series expansion method we can easily determine the inverse z transform. uh, okay, so here this is the another kind of method that we can
Uh,
adopt. Yeah.
yeah, hello, sir.
Yes, yes.
Can you hear me?
Yes, yes.
Yeah. So in this case, there is only numerator.
Hmm.
So there are no poles. So we should not worry about ROC, right?
Yes. ROC will be
Entire Z
entire
plane.
jet plane. Yes.
So yes. So if the Z transform involves only numerator,
Hmm.
then ROC will be entire Z plane, and we can simply follow this method.
Yes, yes.
Okay, sir. Thank you.
Yeah. So, like, here is the one more example. So here, this x of z is given to us. That is log of 1 plus uh, a z raised to the power minus 1. Okay, so for this uh, z transform we have to determine the inverse z transform. Okay, this z transform is basically given to us. Now we have to take an inverse problem here. So for that we will use the power series expansion, because as we know that log 1 plus x is defined as x minus x square by 2 plus x cube by 3 plus x raised to the power 4 by 4, sorry, this will be minus plus dot 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 and so on. Okay, so uh, yeah, we can sum up this coefficient and write this expansion as summation n is equals to 1 to infinite minus 1 raised to the power n plus 1 a raised to the power n z raised to the power minus n by n. Okay, so you can put the value of n here in this function. Okay, so you will get this series. Okay, so now you can see here that we can easily compare uh, this x of z uh, with the z transform, like summation n is equals to 1 to infinite a n z raised, sorry, xn z raised to the power minus n. Okay, so from here we can see that this xn is equals to this term. Okay, so uh, we can say that the inverse z transform of this x of z is written as minus 1 raised to the power n plus 1 a of n by n, where n is greater than equals to 1 and 0 otherwise. Okay, so that's how uh, you can determine the inverse z transform by using uh, this power series expansion method. Okay, now moving ahead, here is the another method by which we can determine the uh, inverse z transform. So this is also power series expansion method, but here we will use division method. Okay, so like for right sided sequence. Okay, so here we are using this method first for right sided sequence, and later I we will also see that how to uh, use this power series expansion method for left sided sequence as well. So like for right sided sequence, as we know that ROC is basically defined as ROC for right sided sequence is defined as this, that is mod of R will be greater than mod of A. Okay, if A is the radius of this circle.
Sir, sir, one more thing. If it is a right-sided, we can also interpret it as a causal, right? Causal sequence.
Yeah,
Causal,
yes, yes, yes,
correct?
yes.
So, yeah, yeah. Okay, okay.
So yeah, power series expansion method. So for as we know that for right sided sequence the ROC will be greater than mod of A, and once you write the z transform, okay, so this will be in the form of negative power of n. Okay, so here for this kind of signal n will be in the form of negative power of n. Okay, so if we are using this division method for determining the inverse z transform for right sided sequence, then we have to determine a series that is basically considering the negative power of z. Okay, so if suppose we have to determine the inverse z transform of this function, okay, where mod of z is greater than mod of A, which denotes that this is a right sided sequence. Okay, so we have to basically uh, divide this numerator by denominator and then form a uh, uh, dividend in such a way that this will give negative power of n. Okay, so here I am dividing here 1 with 1 minus a z raised to the power minus 1. Okay, so first yeah, I am dividing it. So first I am multiplying this denominator by 1, so you will get 1 minus a z raised to the power minus 1. Okay, so once you uh, take negative, so this will cancel and this will come a z raised to the power minus 1. So now to to nullify this factor, okay, we have to multiply uh, this by a z raised to the power minus 1. Okay, so once you multiply you will get a z raised to the power minus 1 minus a square z raised to the power minus 2. So here also you will get a square z raised to the power minus 2. So that's how you can divide this uh, this 1 with 1 minus a z raised to the power minus 1. So you will get this series. Okay, you will get this series. So now you can see that this series is nothing but a raised to the power n u of n. Okay, so like in the previous class we have seen that the jet transform of this function is basically uh, equals to summation n is equals to 1 to infinite. Okay, a raised to the power n u of n. Here if u of m u of n if I am already taking, then this will be n will be equals to 0 to infinite u of n and then z raised to the power minus n. So once you put this value of n here, so you will get this series, that is a z raised to the power minus 1 plus a square z raised to the power minus 2 and so on. Okay, so that's how we can use this power series expansion method, and by using this division method we can determine the inverse z transform. Similarly, for right sided sequence, if we can see here, so as we know for right sided sequence ROC is basically inside this you inside this circle. Okay, so if suppose this is radius a, so here ROC mod of z will be less than mod of a, and here if you expand the z transform, okay, so this contains basically positive power of z. Okay, so here if suppose I am dividing this 1 with 1 minus a z raised to the power minus 1, so we have to generate the positive power of z. Means we have to generate a series that contains positive power of z. Okay, so for that what I am doing, like if this is 1, this is 1 minus a z raised to the power minus 1. Okay, so here for yeah, one more thing, like here if we can further solve this, so this will be z upon z minus a. Okay, so now we can uh, easily divide this numerator with denominator, so this will be z minus a. Okay, so this, so here if suppose this is minus a plus z, we can also write it like this. Okay, so if we want to make the reminder which contains the positive power of object, so what we have to do, we have to first make this first part, that is minus a, as 1. So for that what we will do, we will take multiply this factor by a raised to the power minus 1 and now multiply it by z. Okay, so once you multiply you will get z minus a raised to the power minus 1 into z square. Okay, so you will get this factor. Okay, so now you can again multiply this by a raised to the power minus 2. Okay, so here, yeah, z raised to the power 2. Okay, so you will get minus 1 z raised to the power 2, and this will be minus a raised to the power minus 2 z square. Okay, so this will cancel. So like here you can see that this reminder is basically contains the positive power of z. Okay, so this denotes that this is a left-sided sequence, and by taking the inverse Z transform, because from the previous class we have seen that uh, yeah, like delta of n, the Z transform of delta of n will be equals to 1, and by using the shifting property and not, this will be equals to Z raised to the power n naught. So by using this property we can easily determine the inverse Z transform, and once you get this, you will once you apply this, uh, you will get the final result as minus a raised to the power n u of minus n minus 1. Okay, so by using so here I've shown that by using all these different methods we can easily determine the inverse Z transform if x of z is given to us. Okay, so if you have any doubt here, then please ask. Any doubt?
No, no, sir.
Okay.
No, sir. Please go ahead.
Yeah, so the next topic is initial and final value theorem. Okay, so first of all, why why we are uh, going to study this initial and final value theorem? So like, if a system is given to us, let us say, okay, and we are applying a signal to this system, so what will be the initial response of this system, and what will be the steady state response of the system? That is very crucial. Okay, so to determine this we are generally using this initial and final value theorem. So basically, if suppose instead of x of n you have given this x of z, okay, so so for finding out the initial value or final value, you have to first convert this x of z to inverse, uh, okay, and then find out the x of n, and then what you have to do, you have to put n is equals to 0 for determining the initial value, and n as infinite so as to determine the final value or the steady state response. Okay, so instead of doing this, which is a very lengthy process, we are using this initial and final value theorem so as to easily determine the initial value as well as steady state response of this x of z, if only x of z is given to you. Here no need to use inverse z transform so as to determine first the xn, and then use this n is equals to 0 and n is equals to infinite so as to determine the initial and final value theorem, initial and final values. Okay, so we will use this initial and final value theorem, okay, so as to determine the uh, transient as well as steady state response basically. So if suppose x of k is given to us having a inverse, having a z transform of x of z with a ROC of r of x, okay, then for determining the initial value theorem, that is x of 0, what we will do, we will put limit z tends to infinite x of z. Okay, so by using this we can determine the initial values. Okay, and whereas for final value, what we will do, we will take limit z tends to infinite z minus 1 into x of z. Okay, so this will basically give you the sorry, steady state value. Okay, so by using this theorem we can easily determine the initial as well as final value. So now uh, let us apply this concept on some numericals so as to give you insight that how to use this initial and final value theorem. So here is the example. Okay, and here it is given that Given the following jet transform of right-sided sequence, determine the initial and final values. Okay, so x1 z is given to us, that is z over z square minus 3z plus 2. Okay, so for this, first of all, we will determine the initial value and final value. Okay, so for initial value, as I said, we have to take limit z tends to infinite x of z. Okay, so if you take limit z tends to infinite z over z square minus 3z plus 2. Okay, so like here if suppose I am solving it for you, limit z tends to infinite, we can take we can divide both numerator as well as denominator by z, so this will be equals to 1 over z minus 3z, oh sorry, 3 plus 2 by z. Okay, so now if we put z as infinite, so this will be equals to 1 over infinite minus 3, and this will be 0. Okay, so this basically equals to 0. So 0 is basically the initial value. Okay, and for finding out the final value, we will use this expression, that is limit z tends to 1 z minus 1 x1 of z. Okay, so once you put this x1 of z here, okay, so you will get this expression. Okay, so like here we can directly put z as 1. Okay, so before going ahead, we will first factorize this denominator. Okay, so once you factorize it, you will get 1 z z minus 1 over z minus 1 into z, yeah, z minus 1 into z minus 2. Okay, so this will cancel out and this will be equals to limit z tends to 1 z over z minus 2. Okay, so once you put this value here, you will get minus 1. Okay, so that is how you can find out the final value. Okay, similarly we can determine the initial as well as final value for this x2 of z. Okay, so like for determining the initial value, we will put z as infinite. So if you put z as infinite here, so the overall expression will give 0. Okay, you can put like infinite here, so this will be in the form of 1 over infinite, which will give you 0. So similarly for final value theorem, you have to use this expression, limit z tends to 1 z minus 1 into 1 over z minus zero point 0.1 z minus zero point 0.5 z minus point z plus zero point 0.2. Okay, so now if you put z as 1, so this expression will also give you 0. Okay, so you can use inverse problem as well. Okay, so you can first determine the inverse jet transform so as to find out the x of n here by using this. Okay, and then by putting n is equals to 0 and n is equals to infinite, you will see that you will get the same result. Okay, so this is one of the most important concept, that is initial value and final value theorem. So as to determine, so as to basically check whether uh, how a system basically behaves in initial as well as in steady state case. Okay, so let us move ahead. The next topic is causality and stability criteria. Okay, so uh, like for causality, a discrete time linear time invariant system is causal if and only if the ROC of its system function is exterior to the circle. Okay, so like as we know that if this is the circle. Okay, and if ROC is outside this circle, so this will be causal system. Okay, this will be basically causal system. Whereas for stability, system, we have to check whether this ROC is basically containing this unit circle or not. So if suppose this is my unit circle, okay, this is basically my unit circle, and ROC is like this, it means that it is basically containing this unit circle. Okay, so if this ROC is basically containing this unit circle, then this will be stable. Otherwise, it will not be stable anymore. Okay, so as a summary, is linear a causal linear time invariant system with rational system function h of z is stable if and only if all the poles of h of z lie inside the unit circle. Okay, so if suppose this is my z plane, this is real part of z, this is imaginary part of z. Okay, and and this is the okay, this is the unit circle. Okay, so if this is a causal system, then all the poles should lie inside this unit circle. And if all the poles lie inside this unit circle, okay, then ROC will always contain this unit circle basically. So that's why this system will be stable always. And
Sir, one question.
yes,
In the causality, the first statement, a discrete LTI system is causal if ROC of its system function is exterior of a circle. Is it a unit circle or a circle? Means what?
no unit
Uh,
circle, yeah,
no, no.
it
It is not unit
nahi,
circle,
nahi,
right?
it
It
is
is
not basically a unit circle.
okay. It is a circle of the pole.
Yes, yes, means
Yeah,
maximum value of uh,
the pole.
pole,
Pole.
yeah. Okay,
Yes, yes, yes. Okay, okay, okay.
yeah. So so let us move ahead and take some problems so as to check whether a system is stable or not. So like here we have to basically determine whether this system that is given to us is BIBO stable or not. So like here h1 is given as z over z square minus 3z plus 2. Okay, so like we will first uh, yeah, factorize this denominator. So this can be written as z over z minus 1 into z minus 2. So if we will plot this pole here in the z plane, so one pole is at z is equals to 1, whereas the another pole will be uh, z is equals to 2. Okay, so you if you draw ROC, then this basically greater than this z is equals to 2 circle. Okay, means it does not contain the unit circle. Okay, and that's why this system is not BIBO stable. Okay, any doubt? Okay, so let us move ahead. Here is the next problem. Okay, so here also we have to check basically whether this system is BIBO stable or not. So if we plot the poles here, so in the z plane, so we will get that one pole is at z is equals to minus 0.2, the next pole is at z is equals to zero point 0.1, and the third pole is at z is equals to zero point 0.5. Okay, so we can basically, yeah, so basically we can uh, if suppose we will draw different circles, so one circle will be this, the another circle will be this, the third circle will be this. Okay, so here basically four ROCs are possible. Okay, so let me change the color. So this inner circle is basically, let us take ROC1. Okay, then this is basically ROC2, this is basically ROC3, and yeah, and this is basically ROC4. So we have to check for which ROC case this system will be stable. So let let us take first ROC. Okay, so here as ROC is basically uh, less than zero point 0.1 and it does not contain the unit circle, so that's why this system, for this ROC case, this system is not absolutely stable system. Whereas for the second ROC case where Z lies between 0.1 to 0.2 as well, this does not contains the unit circle. That's why this is not absolutely stable for this ROC case. Okay. In third case also, as Z is lie between 0.1 to 0.5. Okay. So in that case as well, the ROC does not contains the unit circle, so that's why in this case as well this system is not absolutely stable. Whereas for this fourth case where Z is greater than zero point 0.5, so in this case this system is absolutely stable because it contains this unit circle. ROC contains this unit circle. That's why this system will be stable in this ROC case. Okay. So let us now move ahead. So up up to now we have seen the jet transform, that how to determine the jet transform, what are the various properties of jet transform. Then we have seen inverse jet transform, uh, different method of finding out the inverse jet transform, and then causality and stability criteria we have also covered. Okay, so this, up to now we have seen uh, that how to determine the how to analyze the discrete time signal. So there are different other method that we can adopt, that is frequency domain analysis. Okay, so like here also, instead of uh, analyzing the signals or system in time domain, we are basically using the frequency domain, or sometimes it is also called as spectral analysis. Okay, so in case of frequency domain analysis, there is one more important tool which is known as uh, Fourier series. Fourier series method. Okay, so this Fourier series is basically adopted so as to uh, analyze the periodic signal. Okay, this Fourier series is basically using for periodic signal analysis. This is not useful for non-periodic case. For non-periodic signals, we generally use another tool that is known as Fourier transform method. Okay, that we will see in the upcoming lectures. Okay, but for here we are considering that the system is periodic or signal is periodic. So in this case we will use the Fourier series method. Okay, so in case of Fourier series method, any periodic signal is basically represented as a linear combination of sine and cosine signal or complex exponential of different harmonics. Harmonics means set of frequencies. Let us say f naught is basically the fundamental frequency, then twice f naught, thrice f naught, and so on. Is these are basically the harmonics. Okay, so uh, just a moment. Yeah, so basically, this Fourier series is just an approximation of converting a non-standard signal into a standard signal and then analyzing it. Okay, so what are the various advantages of using this frequency domain analysis? So we can easily find out the spectral width. Okay, means we can check whether this signal will work for from this frequency up to this frequency. Okay, and we can easily find out the steady state response where for a periodic input signal, okay, by using this frequency domain analysis. Okay, so that's why we are using this Fourier series Fourier series analysis from from now onwards. Okay, because frequency domain analysis is very important. Okay, so let us move ahead and see that how to define Fourier series for a signal x of t. Okay, so if so first one is the complex exponential Fourier series representation. So if any arbitrary periodic function x of t with a fundamental time period t naught is given to us, so this x of t is basically represented as x of t is equals to summation m is equals to 0 to infinite d of n e raised to the power j n omega naught t. So here this is basically n. Okay, so that's how we can represent any signal as a combination of complex exponential. Okay, so this d of n is basically the exponential coefficient, okay, which we can determine it as dn is equals to 1 over t naught into x of t e raised to the power minus j n omega naught t into dt. Okay, so by using this expression we can determine the exponential coefficient. Okay, Fourier series coefficient, and here omega naught is basically the fundamental frequency, angular frequency, which is defined as omega naught is equal to 2 pi over t naught. Okay, so that's how we can represent any complex signal as uh, a combination of or as a set of uh, as a linear combination of basically the complex exponential. Okay, similarly, the next method by which we can represent any signal is the trigonometric Fourier series representation. Okay, so like in the previous case we represented this signal as linear combination of complex exponential. So similarly here we are trying to represent the signal as a combination of basically sine and cosine. Okay, because sine and cosine are the easiest function for analysis. Okay, so that's why we can also represent this x of t as a combination of sine and cosines. Okay, so for representing any signal in form of trigonometric Fourier series, we will use this expression, that is x of t is equals to a naught plus summation n is equals to 1 to infinite a n cos of n omega naught t plus b n sine of n omega naught t. Okay, so here a naught is basically representing the average or mean value. Okay, so this can be represented as 1 over t naught integral x of t dot dt, and an is basically the coefficient corresponding to cos term. Okay, and this can be easily determined by this expression, that is 2 over t naught integral x of t cos of n omega naught t into dt. Similarly, b of n can be find out as 2 over t naught integral x of t sine of n omega naught t into dt. Okay, so that's how we can represent any signal in the form of trigonometric Fourier series. Okay, so let us now move ahead and see the relationship between the complex exponential and trigonometric Fourier series coefficient. Okay, so as we know that from uh, trigonometric Fourier series can be represented as x of t is equals to a naught plus summation n is equals to 1 to infinite a n cos of n omega naught t plus b n sin of n omega naught t. Okay, so now we will use Euler's identity. So we know from Euler's identity cos of omega t is written as e raised to the power j n omega naught t plus e raised to the power minus j, sorry, this will be, yeah, or we if we are taking n here, this will be n omega naught t by 2. Similarly, sine of n omega naught t can be represented as e raised to the power j n omega naught t minus e raised to the power minus j n omega naught t over 2j. Okay, so we will basically put this Euler identity here. Okay, so once we put and simplify this expression, we will get x of t as a naught plus 1 by 2 summation n is equals to 1 to infinite in bracket a of n minus j b of n e raised to the power j n omega naught t plus 1 by 2 summation n is equals to 1 to infinite a n plus j b n e raised to the power minus j n omega naught t. Okay, so now from from complex exponential Fourier series representation, as we know that x of t can also be written as summation n is equals to minus infinite to infinite d of n e raised to the power j n omega naught t. Okay, so now we can split this summation as summation n is equals to yeah, summation n is equals to minus infinite to minus 1 d of n e raised to the power j n omega naught t plus summation n is equals to 0 to infinite dn, or you can also split it as 1 to infinite dn e raised to the power jn omega naught t plus d naught. Okay, so now you can change the variable n as summation n as minus m. So this will be m is equals to yeah, this, or you can directly replace n as minus n. So this will be n is equals to 1 to infinite d of minus n. Okay, e raised to the power minus j n omega naught t plus summation n is equals to 1 to infinite d of n to the power j n omega naught t plus d naught. Okay, so now you can compare these two. Okay, so once you compare, you will get that the uh, relationship between the complex exponential Fourier coefficient and uh, trigonometric Fourier series coefficient that you will obtain is defined as dn is equals to a naught when n is equals to 0, dn is equals to 1 by 2 an minus j bn when n will be greater than equal greater than 0, and dn will be equals to 1 by 2 a of minus n plus j b of minus n when n is less than 0. So uh, one can ask that what is the purpose of using this relationship. So if suppose a naught an and bn is given to us, so instead of uh, using a long procedure so as to determine first x of t and then determine dn, okay, we can use this relationship so as to directly determining the value of dn. Okay, so that is basically the purpose behind using behind uh, checking this relationship between complex exponential and trigonometric Fourier series coefficient. Okay, so here is the problem. Okay, so here basically we have to calculate the trigonometric Fourier series coefficient for a periodic signal x of t, which is defined over a time period t naught is equals to 3 as follows. Okay, so x of t is basically defined as t between -1 to 1, it is defined as t plus 1, whereas from 1 to 2 it is equals to 0. Okay, so let us first plot this x of t. So once you plot this value of x of t here, so you can see here from -1 to 1 the value will be equals to t t plus 1. Okay, whereas from 1 to 2 this value will be 0. So as this is a periodic signal, so this signal will repeat itself after every time period. Okay, so this is basically the time period t naught, which is equals to 3. Okay, so this is basically the, yeah, this is basically the signal xt. Okay, graph of signal of xt. So now let us determine the coefficient, Fourier series coefficient here, trigonometric Fourier series coefficient. So as we know that first coefficient is the DC coefficient, that is a naught, which is defined as 1 over t naught integral x of t dot dt. So this will be here t naught is 3. Okay, and we can integrate this function, and now after integration you will get 2 by 3. Okay, so I am not integrating, basically this is very easy integration, so I am leaving this for you. Okay, so now the next task is to determine the value of an. Okay, so for determining the value of an we will use this expression. Okay, that is 2 over t naught integral x of t cos of n omega naught t dot dt. Okay, so basically I am taking here the integration from -1 to 1, because from 1 to 2 the value is already 0. So that's why I am taking here integration limit from -1 to 1. Okay, so once you solve this, the value of an that you will get is 4 sine of n omega naught over 3 n omega naught. Similarly, for bn we will use this expression, and once you solve this you will get the value of bn as this expression. Okay, so now you have to just put the value of an, sorry, a naught, an and bn here. Okay, and yeah, this is basically the Fourier series representation of this periodic signal that is plotted here in this figure. Okay, so now this is the last slide. So up to now we have seen that how to represent any signal as a as a combination of, or a linear combination of complex exponential, or set of harmonics of cos and sine. Okay, but the thing is, we have to also check the condition for the existence of Fourier series. So for the existence of Fourier series, the periodic signal must satisfy the following three conditions, which is also known as Dirichlet condition. Okay, so first condition is the signal is basically absolutely integrable over its time period. Okay, so like here, if we are considering this figure, so for this time period from -1 to 2, this signal x of t should be yeah, this signal x of t should be absolutely integrable. Okay, then only this Fourier series will exist. So this is the first condition. Now the second condition is bounded variation. It means that x of t must have finite number of maxima or minima for its time period. Okay. Similarly, the third one is the finite discontinuities, that is x of t must have finite number of discontinuities over its over its one time period. Okay, then only the Fourier series will exist. If a signal x of t is satisfying all these three conditions, so the Fourier series will exist. It means that if these conditions are satisfied, it is guaranteed that the perfect reconstruction is obtained from the continuous time Fourier series coefficient, except at a few isolated points where the function x of t is discontinuous. It means that if x of t is basically satisfying all these three conditions, and if Fourier series exists, then we can also reconstruct the signal. Okay, and if this condition will not satisfy, then we cannot perfectly reconstruct the signal from its Fourier series. Okay, so that's why these conditions are very important. And one more important thing is these conditions are sufficient condition but not necessary condition. So like there are some signals like sine 1 over x. Okay, so in the time period where x from 0 to 1, okay, even if uh, this this function is basically uh, satisfying this absolutely integrable bounded variation and finite discontinuities, the Fourier series will not exist. Okay, so that's why for certain signals this condition will not work. So that's why we we say that this condition is basically a sufficient condition and not a necessary condition. So for uh, for perfectly reconstruct the signal from its Fourier series, it is necessary that this three condition is basically satisfying. Okay, so I hope this class is informative to you. So this was the last slide. So we in the next class we will uh, see the continuation of this Fourier series. We will solve some more numerical. Till that, thank you.